Okay, welcome back. Okay. So where are we? We know how, or at least we're learning how to like express ourselves to Spark in order to say, hey, I want these calculations done, which is of course not radically different. Like I know, like I didn't use these words the same way, but when you're doing like pandas work or whatever, I guess I don't have much pandas work in this code, but well, yeah, I do. Sorry. This is fundamentally, dear pandas, I would like you to do this calculation, please, and then I would like you to do this with it, and then I'd like you to put it there. It's the same thing. Like I tend to think of it. This is like a statement in a programming language, and it runs. With Spark, I tend to think of it more as a like. This is a polite request to Spark. Hey, can you do a whole bunch of mod 10s for me? Thanks. You get those done on whatever computers in whatever way you can as soon as possible, and then we'll carry on. The partitioning matters because that determines how much concurrency I get, and the only way that we've seen so far to deal with that is one file becomes one partition. And that's not 100% true, but we are never going to see a case. We are never going to see a case where that's not true. So, like if I look on the compute cluster and I look at, well, like this smaller input directory for this first problem, I see 4 files. Okay, that means I can have the biggest compute cluster I want. I'm only going to be using 4 executors. Well, okay, that's fine. That's a really small data set, and I'm totally cool with that, right? But I want to have that thought, or I want to at least have that in the back of my head somewhere. You know, one of the things that's on the compute cluster is the Reddit comment corpus. That is, God, it's so big. It's a real pain in the butt to deal with. But it's, I don't know, however many files that was, and I'm not quite up to date on it. It's okay, 236. I'm out of date on my slides. I'm presumably 36 months out of date on my slides, but they're stupid files. They're just horrible files to work with because, of course, in the first month, nothing was happening. Like this is not a lot going on in Reddit in December 2005, and then, you know, as time has gone on, there's been more going and more happening. And now this is a 39 gigabyte file. Okay, that's too many, that's too few partitions for that much data. And this is bigger than I'm comfortable with being in one partition, because it means somehow, like I've just got effectively a for loop at some point. If I want to do some calculation on this over 32 gigabytes of data, that's going to take way too long, and that's going to be really annoying. I hate this partitioning if I'm a Spark programmer. If I'm somebody distributing these files, it makes total sense, right? Each month release a file and compress it in some really aggressive way. Great. What actually is happening, like what I would actually do to this data and have done to this data, oh, right, it's arranged. It's arranged by month, by year and month. God, these file names are just that much too long. Is each one of these got put into a partition basically this way. It's just like, take the file, make it into individual files that have enough lines to be about whatever size that was. This is not awesome. There's no concurrency in this story, but just dealing with HDFS can be a bit of a pain. But that's not what we're concerned about here. Maybe you can control it. You can, you know what, actually? So I have been, all the way through here, I've been doing Spark submit and handing it a Python file. And that's totally fine. That's usually what you want. But maybe I'll do PySpark is the Python interactive shell, the REPL, except in a Spark world, where the Spark session object already exists. So I can do this here. Well, so that is a data frame with one column, and that column is an integer. Okay. I don't think, yeah, I can't even ask a data frame how many partitions it has directly. You can get there. Storage level, yeah, I don't think any of these methods. Oh, it's stat dot something. Yeah, okay, that's summary stats. Yeah, like I don't think there's any methods there that will tell me even how many partitions I have. I can ask about the underlying RDD object. That's underlying is the wrong term there. But I can convert it to another type, and that other type can tell me how many partitions it has. That's kind of gross. You can inspect things. I forget what this function that I wrote that does some stuff. It's weird and it's not beautiful either. Honestly, if you want to know how the data is arranged in a data frame, wait, I would do that. Yeah, so that just created this thing called ints. Oh, I now realize I have 6 partitions and they're all exactly the same size. Well, it's because, yeah, like this thing just creates a 0 to n minus 1. So it takes an argument for how many partitions it has, and okay, fine. Like this isn't usually where my data is going to come from, but if it is, sure. There are some operations like a group by that we'll talk about real soon now. Like if I do a group by, there's just a thing. There's just a setting for that. That is, the default is 200. It's in here somewhere. And that's a fine default. You know, you probably, I guess, let's put it this way. If you have more than 200 CPU cores available, there hopefully is somebody around who can update a config file appropriately. Okay, fine. This is weird. And again, I think this is now not real. Spark has gotten a little bit smarter about the number of partitions when it does this kind of thing, and it will create fewer partitions because it will realize like, oh, hey, there's not much data here. 200 partitions is crazy. I'm allowed to use it less if I want. But almost always what we're going to see is one file becomes one partition. And maybe I'm happy with that. Maybe if I'm not happy with that, what I should do is fix my input data. Like I should rearrange the input files to make them more or fewer, more evenly sized partitions, whatever it is. Maybe I have to fix the data frame after I get it. There's a method that is just like combine existing partitions into fewer. It doesn't do it well in a sense. Like, you know, this data frame that I constructed, when if it had these weird imbalanced partitions, like what I would imagine would be that like I would combine those together and get rid of the empty partitions. What I actually got was the 2 big partitions got combined into one even bigger partition, and that sucked. But probably if I'm doing that, the problem is I have way too many partitions for my situation, and so probably I don't care very much, but maybe I want to do this, but probably not. It can help in this kind of scenario where, well, even here, so the code, again, this is code from this week's assignment. This is calculate something mod 10. So I know there's 10 unique values in this column, because that's how mod 10 works on integers. And then we group by that. Well, if I'm going to group by that number, the number of rows I have in the output is the number of unique values in that column, which is 10. Okay, fine. Like in that case, in fact, even saying coalesce to, like 10 is a really small number. In this, by now, if I want to turn this into one output file, that would be totally fine, right? I did 2 in the exercise just because I want you to remember 2. Like this is multiple files. It's not a single file in a single directory, which is kind of the impression you might get if I put a 1 there. It's multiple files in a directory, and that's actually what I want. So yeah, like I don't think this is a bad idea if you know something really strong about the number of rows you have left. Because, okay, like again, I just went through this whole story of the partitioning determines the concurrency you have, and if you have too few partitions, you have not enough concurrency. If I have 1 partition, which is what happens after a coalesce 1, I have no concurrency. I have everything, like one executor process is now going to get all of my data. If I know there's less than 1,000 rows, yeah, whatever, sure. If I do this just because I feel like I like having a single output file, but I actually have a kind of big data set, I'm just about to run out of memory, or I'm just about to wait long enough that I think Spark is inherently slow or something. This is a dangerous thing to do if I don't know something like that. If you really do want your partitions to be different, and what questions do I give you guys? No, okay, I'm not spoiling it for you guys. I have a partition I give to the Big Data Lab, the professional master's program, where I just give them some input files. I'm like, do the thing, and then I ask, hey, why is the thing really slow? And it turns out because the partitions are radically different sizes. And so one worker process is doing a huge amount of work, and one worker process is done in 1/10 of a second. Maybe then it's worth it to say, okay, you know what, my partitioning is really dumb. It's really bad. This is not a free operation. Like this is a little bit expensive, but maybe it's worth it to say, okay, rearrange. And if it was real data, you know, I wouldn't say 4 there. I'd say 400 or something if it was actually a big data set. Well, if all I'm going to do is print out the number of records in each partition, there's no way this was worth it. That was crazy. If what I'm about to do is like write 100 lines of code that do this and that and the other thing to that data set, maybe it's worth it to do this work first so that everything else is done with like beautiful, perfect concurrency. This is, well, it's a course rule because I say so. It's also genuinely something I do in my own code. In fact, I did it there. Here, I wrote this code in the template for y'all. And okay, I know that up here, when I start, I have 1 partition for each input file. There's 4 in the smallest data set, and what did I say? 40 in the big data set or something? Still not that big a data set, fine. And then because I have those 40 partitions, this and the code that you add in here is going to be done concurrently on 40 partitions, and that's great. And then the group by work and the aggregation work, okay, there's some moving stuff around the network that we'll talk about later, but I still get pretty good concurrency out of it. I still get pretty good concurrency here. And then at this moment, I'm saying, okay, take all those things and smush them down into 2 partitions. And if I had a huge data set here, I've just done something incredibly stupid. So I have left that comment for myself that I know this. I know this because I know how this works and I know how this works. Mod 10, 10 unique values. Group by, 1 row for each unique value. It's mathematically impossible that there's more than 10 rows here. So I know that's safe. Like, you know, like in this code, presumably if my data frame called weather data is what it sounds like it is, if I do a group by year, I've got 1 row left for each year that humans have been collecting weather data. I know that that's a relatively small number, and I no longer have big data after this group by. It depends what you're doing. These numbers are, oh no, I think I did actually update this number not too long ago. I actually checked, right? Just how many unique subreddits are there? That determines how many rows are there after that aggregation. okay, like I think about that number and I think about how much concurrency do I need to work on that much data, and I put that number there, or in a repartition. But I think you have to leave that comment. Like I said, I genuinely do it myself. I still believe there is no correct number of partitions for a data frame because it depends, right? If all I'm doing is an add one, easy. If I'm doing some big horrible calculation, well, maybe I want smaller partitions so that I can kind of keep track of what's going on. I can see the progress a little better. One of the things I like in the Spark web front end that I saw was when that progress bar was like 5 out of 10, that I have 10 partitions and 5 of them, the operations on 5 of them had been completed. And I think what we saw there was the other 5 were in progress at that moment. Okay, so the number of partitions also controls sort of how much granularity you have in that progress bar, which maybe matters sometimes. You just want to keep an eye on things. Okay. The problem with this, like a data frame is partitioned, is it's an abstraction, right? Like you don't usually think of it. Usually my sort of mental picture of a data frame is just a single data set that is completely like uniform. And I'm just going to do this to each thing. And I'm going to do a like times number, whatever on this thing. And that's just something that in my mind is for each. For each X value, multiply it by 123. For each ID value, mod 10. And usually I can get away with that. The problem is I have to have somewhere in the back of my mind that it's actually a bunch of different data structures. It's all of my data broken up into some number of partitions, and that the concurrency is happening on those partitions. But there's a real compute cluster here that's running on real hardware and has a real network in between those computers. Okay, so if what I'm going to do is multiply by 123 or whatever, fine. This computer can multiply this number by 123, and this computer can be doing this one, and this computer can be doing this one. And okay, maybe this computer is done first because it has less data. This one's going to take a little longer. Okay, maybe I'm unhappy with my partitioning because of that. But, well, I guess the question, the thing I'm getting at here is, what if things are not embarrassingly parallel? What if I want to do a dot repartition and I want to make all of these partitions, like I want 5 partitions that are all perfectly the same size? Well, I've got to move most of my data set over the network to make that happen. That's a real cost. I should be thinking about whether or not that's worth it. So anything that has that shape is a shuffle operation. Anything where basically you can't look at a single partition and do the entire operation without coordinating with anybody else. So like I've sorted here. So sort must be a shuffle operation, because if I started here with 40 partitions, well, maybe the smallest value is in this partition, maybe it's in that partition, maybe it's right beside the biggest value, right? Who knows? So the data set has to be moved around the network because, well, of course it does. If I want to get the data in order, sure. If I want to make all my partitions perfect, I have to move the data between executor processes, and that means there's a network in the way. Well, networks are not infinitely fast. They're certainly not as fast as like the memory bus on your computer. I mean, it's one of the things I love about Spark, right? That I get to write this beautiful high-level description of what I want done, and it just works. That's great. I also love, because I'm this kind of person, that I have to remember what's really happening and that there's real computers in the way, and that there's like a systems question now of like, yeah, but what did I just ask for and how fast can it really be done? Maybe I have to think about that. I talked to an old student at one point who basically said, we can't sort. Like whatever data set they were talking about, it was something like all of the company's log files, right? Like it was this massive data set. You know, I'm sure it was organized chronologically because that's how it was built or whatever. But he said, yeah, we can't, like, you know, if we could sort it by customer or whatever, but no, we can't. Like conceptually, you can sort it by a different thing. But the simple fact was their data set was so big that the sort was not practical. They kind of just had to, in the Spark terminology at least, just avoid any shuffle operation and do only these embarrassingly parallel operations that can be done concurrently without having to move all your data around. It can happen. Remember, by the way, when I said back here, big data is what happens when you have so much data, it's annoying. That's annoying. Like being able to type like .select and it goes fast and .sort and it goes slow, even though they look kind of equally difficult, or possibly having so much data that sorting it is maybe impossible, maybe something you have to plan ahead and just say, okay, well, we're going to sort this weekend. Nobody's allowed to touch the data until that's done or whatever. That's really annoying. And it can be the reality here. How much data are you moving? How much does it have to be moved? This can be something you have to worry about. Yes, good. Thank you, Pass Me, for getting this terminology in there. A shuffle operation is the thing where you have to move data around and rearrange your partitions somehow. A pipeline operation is the good one, the one where you don't have to rearrange your partitions, the thing where often you can just deal with one row at a time, not even a whole partition at a time, right? Like if I want to do a .select, like over in this code, I don't have to look at row 2 when I'm multiplying the thing in row 1 by 123. I can do everything in this story. I can read one line from a file. I can multiply one number by 123 and mod 10 a different number. I can do all of that one row at a time. I don't even have to have my data set in memory. By the time I do the group by and then the aggregation, I do have to move data around. That's a shuffle operation. So if I have a pipeline operation, I'm definitely happy. If I have a shuffle operation, I am maybe not sad, but I have to think about it. So the group by operation that, well, I just talked about and it is in your lab 9. It's definitely a shuffle operation. Like definitely I have to move data around because again, I have a bunch of partitions here. I do this calculation and there are going to be there's going to be some rows that have bin equals 0 on this partition and this one and this one and this one, and on this computer and that computer. They're going to be all over the place. So if I want to take each one of the things with bin equals 0 and add up the x and count the number of rows, well, I definitely have to shuffle, but not as badly as you might think. So let's do this. I am going to leave that. Okay, I have this. So this is if you like on the course website, technical Spark skeleton. It's this code. This is just a code that I use to start a Spark program. You're welcome to. You're welcome to not. And like I said, I do this because I can, if I want. I'm not a huge fan of my line breaks here. Well, I can do something like this, right? Like if I imagine I've written some more code below, I can do this. I can just do a values.show and then bail out of my function, and no great pain, no great difficulties will occur. Okay, I don't need these command line arguments because I don't have any in this code. Okay, I am here. Okay. Okay, what am I doing here? I am, well, I'm creating just a range of 10,000 values. I'm only looking at 20 of them here. And for each one, so for the number, like the first row is 0, the next row is 1, the next row is 2. I guess, and the column heading is ID. That's just part of what the range function does. calculate thing mod 3, calculate the length of the thing when it's represented as a string. So how many digits are in it? Num digits, good column name. You know, this is, yeah, like there's 2 digits in 10, there's 1 digit in 9, sure. Keep the column and then calculate the sign of the column just because I wanted another column in my data set. Okay, one, I can kind of get a lot done this way. Everything I have so far is embarrassingly parallel. That's great because select, again, it's a 1 row at a time kind of operation. 6 partitions, sure. I don't know. Maybe if I had more data, I would want more partitions. What is that, 1 million? 1 billion? I feel like there's a certain talent to just deciding like, hey, what's a small number? Is 1 billion a small number or a big number? I think it'll be fine. I think what I'm doing here is pretty cheap. Spark is pretty fast. I'm going to go with 1 billion. We'll see if I regret that in a few slides. So the operation I'm doing here is a group by on this column. So again, this is the thing where I know there's only 3 unique values here because I did mod 3 here. And because I want to make this point, people get this wrong all the time. I get it wrong all the time. This is not data. It's not data in pandas. It's not data, the analogous pandas code. It's not data in Spark. I hate that this is a method because this looks like a data frame, right? It's like group by this. But saying group by is just some statement about how I'm going to arrange the data. I'm going to aggregate the data and I'm going to take all the values that have mod equals 0 and I'm going to put them together. What I haven't said yet is put them together how? This is not a calculation. It's not even a calculation. It's the first half of a description of a calculation. If I want to actually describe the calculation, it's something like, okay, and when you get things with equal values for this column, I want you to look at this column and count it. I want you to look at this column and add it up. That's a calculation. That's something I can actually do. Which makes me think, by the way, I don't think this should be a method. Like, I think this should be one method call that has 2 arguments, basically. I think if I was in charge, it would be this, because this is one, it's grouped by this, and to do this calculation is one thought. But it's not one method call anywhere because SQL has infected our brains. Because in SQL, you say group by over here, and you say the aggregation function in way over there, and people think it's a different thing. It's not. Anyway. Okay, so I can spell this aggregation this way. I have this other slightly more different way to do it. They're both equally fine. I'll get the same result either way, give or take some rounding error or whatever. No, I think there was exactly the same. It's why my default thing has this import, because you use these kind of things a lot. Or right, like I just group by one thing there. You can group by these 2, and now the question is, how many unique values are in pairs of numbers from these columns, right? So there's a 1, 2 and there's a 2, 2 for the pair of those values. So now the number of unique rows I have, or the number of rows I have in my output, is the number of unique values for mod common num digits, the 2 together. And what did I do? I did count and sum on the last slide. I could do average and max on this slide, sure, right? I guess I don't know the order. I happen to get 1, 2, 3 here. I don't know what I'm going to get in general. Which is why I put that sort in there. Maybe I'm going to not. Oh, what did I just do? Oh, that's not what I meant to do. Anyway, yeah, I don't have any strong, and I think it's not defined. Like, I think if you ask, like, hey, what's the order of things after a group by and an aggregation in Spark? I'm pretty sure the answer is none of your business. It'll be in whatever order we decide to put it in. And that seems to be what I got here. I got an order. I got an order that like somebody, like whatever implementation of group by and aggregate Spark has, this is what it did. And I guess, sure, if I want it to be in a specific order, I'm gonna sort it myself. That's fine. I'm allowed to ask for it. But I guess the thing is, I now know that sort might be expensive. I now have the choice to decide. I want it to be done, or I don't care. So definitely the aggregation is a shuffle operation, right? I do have to get data from over here to over there. I can ask a little bit about it. And I don't know if this is a thing that people do in the databases course or something. You can do the same thing in most SQL databases, if not all. You can say, like if you're saying select, I guess it doesn't really matter. This kind of thing, right? If you have some question about like, hey, what's the performance going to be, or how does the join get done? Whoops. You can, I think it's standard syntax to put the word explain before select, and then instead of doing the operation, it will tell you how it's going to do the operation. And you can do the same thing in Spark. It's just dataframe.explain, and you get this like wildly, well, I don't say unreadable, not radically friendly. I'll go with this one. Same thing, I guess. So I have to read this bottom up, which is a kind of weird way to look at it, but okay. So start by creating the range. Oh, I guess 1 billion was a small number. To remind ourselves there. And then, okay, I'm gonna calculate the mod 3, calculate the length of the string, calculate the sign. I'll keep the ID value and calculate the sign. Right? Sure, that's my select. Okay, and then some funny stuff happens. And the thing I wanted to point out here, well, actually, yeah, it's a good point that in my code, like I just asked to explain result, which is this data frame. But somehow it knew its origin, right? It knew that it came from this range and then this select, and then we did the group by in a couple of steps. That's interesting. Maybe we'll have to talk more about that. And then in the group by, there's, again, reading bottom up, it's do something called partial average and partial max, and then exchange, so shuffle, and then calculate the average and the max. So what I would read from that, and it's the same kind of thing happening here. Yeah, same thing happening here. A different Spark version. You never quite know if they're going to change something, but what's being told to me here is combine rows that have the same this and calculate that within this partition. So like I am going to imagine that partial max is almost certainly the max within the partition. And then the partial average is probably the sum and the count within the partition. And then take those things of each value within the partition. So, well, how many rows do I have here? Like I probably have something like 35 rows, or either 30 or 40 rows. Oh no, I have more because my numbers are bigger. But anyway, I have like 100-ish, like I don't have a 5-digit number of rows here anymore. So let's say 100, just because it's easy to remember. For each partition, I'll have 100 rows or whatever that are sum and count, and then the max within the partition. And then for each partition, take my small number of values, move those around the compute cluster, get the values where mod equals 1 and num digits equals 3. Get all of those together and then finish calculating the average and finish calculating the max. Okay, so that first step happens as a pipeline operation, right? Like it happens without any shuffling, without any data movement. And then I get down to a quite small amount of data. That very small amount of data gets moved across a compute cluster, and then we finish getting the right answer. At least that, you know, I'm reading a lot into some pretty dense text here, which is not documented anywhere, by the way, but that is what's going on. I'm doing this partial aggregation before I move data across the network. So I have very little data to move across the network, and then I'm finishing up. Okay, cool, right? That sounds great. That's what I want. And that means if I was on the compute cluster here, even if I add a bunch more zeros here, the amount of, well, maybe I'm asking for a lot of computation to do all of these things, but the amount of network traffic I'm implying by this operation is really small. Let's not go too crazy here. Okay, I think that's clever. I think it's useful to see this, right? Like just being able to look at this data frame and being able to explain like, hey, how are you going to calculate this? And then again, like I'm not going to pretend it's easy to read this, but you can kind of, it's like reading a programming language that you don't know. Like you can do it. Yeah, kind of, right? It's like, okay, I know what I'm trying to do is this and this and this. And I guess, yeah, I can see that that's going to happen. And then I'm going to do this, right? You can kind of sort out what's going on, even if you don't know exactly what the syntax is. And I know there's a pretty small amount of data movement, or I can infer that, and I can actually see it if you really want to like start looking. Point being, if I wanted to sort the data frame, I don't get that. If I have a billion rows and I want to sort them, I just have to move all billion rows around, or almost all of the billion rows around. Same story for a repartition. Not every shuffle operation is created equal. Yeah, if I did want to I might want to sort by sign. That is a much more expensive operation, I imagine. Certainly on a compute cluster it would be, because I have a lot of network operation in the way. I can kind of infer the sorting algorithm here, right? Because what I'm seeing here is like do the before, you know, do the work before, like to get the data that I'm going to sort, and then do something called range partitioning on this value in 200, I'm going to guess, partitions. That's a quicksort. That's a quicksort. Like when you do quicksort, you choose one partition and then you get one partition value, and then you pivot. That's what it's called. I'm a computer scientist. You choose one pivot and then you get two partitions. Okay, they are choosing 199 pivots and getting 200 partitions. So you do have to move the data around the network, but then you get, you know, all the small values in this partition, the next smallest values in that partition, and then you finish sorting within the partition. Is, again, I'm reading a lot into a very small amount of text, but I'm pretty sure that's what's going on. It's the only way I can read these words into a sorting algorithm, I think. Or yeah, why is the partitioning perfect? Well, round robin partitioning kind of implies like take the first row, put it in partition 0, take the next row, put it in partition 1, take the next row, put it in partition 2, and just kind of keep doing that up to partition 99 and repeat. Okay, that's probably what happens. That's probably why I get really nice partitions. It's also why, if I'm on the compute cluster, I've implied a huge amount of network traffic here, and maybe I'm not okay with that. Yeah, okay. A few minutes left here. I think I'm glad I get to talk about this before leaving for the week. I think Spark feels weird in a bunch of ways here. One way that it felt weird was I added this line to sort this huge data set, and it did not make my code run very much slower. It seems a little weird to sort of create this data frame just so I can throw it away to calculate this data frame, just so I can throw it away and create this next data frame. Like, it doesn't seem like I'm using a lot of memory there. Coalesce is kind of dumb. Turns out it's kind of dumb because it doesn't actually know what the data it's working on. And again, why are these execution plans so complete? I don't think, like, this result data frame, I don't think it should, like, it doesn't look like it should know that. I mean, obviously I think it should know that because I wrote the next slide, but it doesn't seem obvious, I guess. Yeah, why is this code so fast, right? Or like, why is this code so fast? This definitely doesn't seem like, what'd I do? Oh, I actually exceeded the size of a 64-bit integer. Okay, fine, I'll be a little less dramatic. That didn't take very much time at all, right? Even though I talked about the sorted sign, like, it seems like I should have to calculate 10 trillion or whatever that is signs and then sort them, and that didn't take long at all. It didn't take long enough to have done anything. So I guess the title of the slide gives it away, unsurprisingly. So if you know the term lazy evaluation, it's that. If not, what it means is talking about a calculation in Spark doesn't cause the calculation to happen. All that I've done here, like if I create something called sorted here, that's a keyword. If I do that, I'm not actually saying to do that calculation. All I'm saying is I would like to express this calculation to you, or I guess in other words, I want you to create this execution plan, right? Like, the execution plan is the result of typing that code. Evaluating it, that hasn't happened. Like, in the code that I have in my editor window here, these numbers never exist. These values never exist. They never get sorted. All that happens in this code is Spark plans how it would do that calculation if it had to. It doesn't do it until it absolutely has to. Even when I call .show, I think if I call .show on that data frame, it would be a huge amount of work because it has to sort and get the 20 smallest values. So that means it has to calculate all the values. But if I didn't sort, okay, that's a bad variable name now, but you know, you'll forgive me. Now all it has to do is calculate the first 20. Well, that's easy. The fact that there's 10 trillion minus 20 values that could be calculated later, I'd say whatever, we could do that calculation later. That doesn't cost anything. This is cheap because I only had to produce the first 20 rows. If I actually materialize the data frame is the term that Spark uses for it, like this is now incredibly expensive, right? If I wanted to by the way, mode equals overwrite will replace the files if they already exist. The default is to not do that, which is totally reasonable. Now I've asked for some work. The show is still cheap. This is not like, I'm not going to let this, I'm going to get bored way before that finishes. So that's why doing this kind of thing isn't bad in Spark. In Pandas, this would be bad. In Pandas, every time you talk about a Pandas data frame, it's actually a data structure materialized in memory. It's a bunch of arrays or whatever. In Spark, when you talk about a data frame, it's just an execution plan. whatever, however big that object is, not enough I'm going to worry about it. The only data frame that would actually get created is the result of the execution plan that I have named df4 in my code. Of course, that's the actually so I guess maybe another piece of just Spark context. The creating the execution plan is something you do in the driver process. Evaluating the execution plan is done in the executors, right? So it's create the execution plan in the code that I can see, and then send off to the drivers, hey, I need you to evaluate this execution plan and create some CSV files. And these are cheap. Having a Spark data frame, even if it describes a terabyte of data, is really cheap because all it really is storing is the plan to create that terabyte of data. Coalesce is dumb because the data doesn't exist when it makes its plan. Repartition does this more expensive thing where it's like, okay, actually calculate the data and send a row here, send a row here, send a row here. It's slower, it's more expensive, and that's why. So that's usually good. And I don't know, if you've taken 3D3, certainly with me, I think with anyone, you would have come across the term lazy evaluation. Lazy evaluation is one of those things that's like, this is awesome, right? I love being able to be very expressive in my code and say like, oh, like I'm going to use a better name than df1, df2, df3. I'm going to call them this. Okay, values is still not a very good variable name, but stay with me. I'm gonna have really nice, beautiful descriptive variable names. I'm gonna have these very careful, readable steps for how my calculation needs to progress and what I need to do, and that's great. My code will be very beautiful, and the lazy evaluation will take care of the fact that I don't have to have all these things, sitting in memory. Where again, in pandas I do. In pandas, every data frame is in memory, and you maybe have to be a little more careful about it. Here's the problem. If I'm going to do something like this, where I have one data frame called values that I calculated on the last slide, and what I'm going to do with it is group by this and put it in result 1, and then group by that and put it in result 2. And I'm going to, I guess, imagine here like .write.csv. Like I'm actually going to do something with a value as I've written it on the slides. Super cheap because I didn't actually do the calculation. The problem is the execution plans have this like common ancestor. So the execution plan to produce result 1 involves doing this and this, which is back here. And the execution plan to produce result 2 involves doing all of that same stuff. I'm going to do that work twice in this story. The work to produce these values has to get done if I write this to disk, and then it has to all get done over again because Spark's not going to keep a temp. Like usually when you write values equal in a programming language, you're thinking like it's an integer or it's a little list or something. This could be a terabyte of data. Spark is not going to keep a temporary value around just because you might want it later. It's going to throw it away. Well, in fact, it's never going to create it because it's just an execution plan that you never evaluated. I have these common steps in these two execution plans because they came from a common source. I now have to do all that work twice and I am sad. So the short version is there's a way to ask Spark to please keep this intermediate value in memory. It's called caching. But we're going to come back to that next week. I'll see you in the quiz and then I'll see you in the lab. Bye, everybody.